Hello, applications students. So we are starting our new unit, Unit 3, and this unit is all about going back to geometry and applying it in an algebraic way. And so we talk about geometry as shapes and things that we can do with those shapes, finding their volume, their area, the distances, all of those things. And trigonometry is a big part of geometry in that way. And now we're talking about bringing it back to a coordinate plane and applying formulas that we've used in algebra, as well as ideas that we've used in algebra to go ahead and tie all of that we know in about geometry and algebra together. This will be our last unit dealing with geometry. We will move on from geometry from here to other more algebraic things. So let's go ahead and get started. The main point of this lesson today is distance and midpoint formula in an IB way. So we're going to talk about those formulas which you've learned in the past. We're going to reassess them, relearn them, and then apply them in IB problems. So your distance formula, when you think of the distance formula, we always have 2 points. And let's, for instance, say that this is 0.15, and let's say that this is 0.62. And we're trying to find the distance between those two guys. And when the formula was created, the formula came to be by thinking of, well, what if we made a right triangle from those 2 points in order to solve for the distance? Well, if I made a right triangle, I could find out this vertical distance by finding the distances between my two y values. The distance between 5 and 2, in other words, the subtraction between 5 and 2, is 3. The distance along here would be the distance between my x values, because all I'm doing is shifting over from the x-axis over. The distance between 1 and 6, in other words, the subtraction between 1 and 6, is 5. So solving for that missing side length, when we only have one missing side length of a right triangle, we know that we are going to be using our Pythagorean theorem, that c squared equals a squared plus b squared, right? So we take these two legs, right, the two side lengths that cover that 90-degree angle, legs, so they're called legs for that right angle, plug them in for a and b, and that equals what we've now called our distance squared. So then in order to solve for that distance, we just need to take the square root of both sides. We take the square root because we're trying to undo that square. So d will be equal to the square root of 3 squared plus 5 squared. Now we can find out 3 squared, 5 squared, add them together, and then take the square root, and we get some sort of decimal here. But that's a general idea of how we're solving for distances and how the formula came to be. So then we start to compare our formula back to this idea, the square root of, and it says the bare bones of the formula is this idea of something squared plus something squared, which feels very familiar in our Pythagorean theorem, the idea of taking a length here and squaring it, and then adding the other length here and squaring it, all underneath the square root. Now, what we put inside these parentheses is just the difference between our x and y values. So I would take my two x values, I'm going to call it x1 minus x2, and that's what we did in order to solve for 5, right? So that's represented over here. And then y1 minus y2 would be how we solved for this length over here. We found the distance between 5 and 2, so we subtracted them. That's all we did. The Pythagorean theorem really just gives you the distance formula. Also, it's in your formula packet, so you can go ahead and reference that there. This is how we find the distance in a 2-dimensional way. When we find it in a 3-dimensional way, it's a pretty logical next step. 3 dimensions means that we have 3 coordinates. You can see below that we're going to deal with 3 dimensions over here. And those 3 dimensions are represented as an x. So we would do x1 minus x2 squared plus y1 minus y2 squared plus, and then z1 minus z2 squared in a 3-dimensional way. The distance formula.